final research lesson due? Oh, where today? Nope, that's not what I want. It's a lot less rugged than your previous research lesson, so you don't have any sources to find or any sort of business like that. So this is really focused on working on and summarizing our ability to recognize source and author reputability. So on our eLearn page, you will find sources already provided for you. And all I want you to do is read through the sources and then using anything you want at your disposal, look up the sources, look up the authors, and you're going to provide me a summary of each and then assess the reputability and the bias found in each source and each of the authors that write each source. And at the end, tell me which source you think is the most reliable or reputable. So make sure that you're looking at that. That's due tonight. And that's your final research lesson. So we're finally done with those, right? It's been a long haul. Make sure you don't miss it. Sad to come this far, and then that's the one that we missed. So keep an eye on that. Also, the last reminder. Nope, I'm not nailing this here. That's the button I want to hit. Woo! Don't forget we have a test coming up. So Jasmine, that's our 9 a.m. TA has her test review session tonight. She's going to be guessing a little bit at all the stuff we're going to go through, so it'll probably be mostly focused on the stuff we've already done. But there is certainly plenty of that. So please make sure to do your very best to go to that. Okay. Hit record for me, Ms. Gallimore. So, on Friday and beyond, we have been working through cell respiration. So remember where we are. We started with one glucose molecule, which had 6 carbons. And we made pyruvate. Okay, and then from there, we made 2 acetyl CoA. And along the way, we picked up 2 ATP and a handful of NADH, right? Some piddly consolation prizes. Okay, so remember, this first step was glycolysis. Bakers. And the second step was the prep step. And that has led us to where we are now. Okay, so now we're in the citric acid cycle, and we just started a summary for this at the end of class, right? So remember, we had said, well, we're in the mitochondria. Remember, the mitochondria is like Alcatraz. Once you're inside, you never leave. We'd entered the mitochondria in prep step. Okay, we had said that we were aerobic. Okay, this is an oxygen-containing step. We had said that because we're going to release some CO2. That was something we learned on the last slide. And also because we're using oxaloacetate, an oxygen-containing compound. Some hidden information for us. Okay, so at the end of class, we had just gone through sort of a summary of what we should expect in our cycle. Okay, it's a many-step cycle, most of which we're not going to worry about the details about. We just want to understand what's going to happen here. Because remember, our goals, right, is to follow where is the energy coming from. That's our goal list, right? What are we starting with and what are we ending with? Where's the energy coming from? Those are the only things we care about. So that's what we're going to focus on. So, okay, we're coming in with acetyl-CoA, right? This is what the prep step is bringing in. Okay. Acetyl-CoA is going to join with oxaloacetate. So that tells us acetyl-CoA plus oxaloacetate. If it's adding to oxaloacetate, that must be what the end of the cycle is. Because that's the leftover from whatever happened before. Okay? So acetyl-CoA plus oxaloacetate is giving me equals citrate. Citrate's what the cycle is known for. This also must be a start to my cycle. So this is the goal then. Right, well, this is our start. Okay, over the course then of our citric acid cycle, a bunch of stuff we don't care about happens. Okay, to go from start to end. Okay, the key is and we know that our citrate, to get citrate, we added acetyl-CoA, right? How many carbons does acetyl-CoA have? 2. Okay. So we know that we need to lose 2 carbons. Okay. When we break bonds, okay, catabolism, we get energy from that process, right? Okay, so that's the whole goal here. We've got a big cycle all set up to get some of that energy out when we do that. Okay? Remember from our visual roadmap, a little bit of that is ATP. But as we're going to find, it's not the most impressive thing we've ever seen. What is super impressive are these guys. We're going to get a ton of coupons out of the deal. We're finally going to see today what the big deal about these coupons is. Okay, this is where we left off on Friday. Any questions before we take a peek at the cycle itself? Okay, so here's our cycle. Like I said, we've slimmed it down to focus on the things we care about. So, here's our acetyl-CoA. Nope. Here's our acetyl-CoA. Okay, so we know that acetyl-CoA plus oxaloacetate, okay, that's the end of our cycle, makes what? Citrate. Good. The only two things we care about. And citrate's not too bad to remember, right? Because that's what the cycle is named after. And oxaloacetate, we want to try to remember, okay, does oxygen as part of its name. That's reminding us this process is aerobic. Otherwise, there aren't any compounds on here. We don't care about them. But there is some stuff on here we do care about. Remember, we added 2 carbons at the start. So we know we have to get rid of 2 carbons. It doesn't happen all at once, but we don't care. We just know we have to get rid of 2. Okay, so that's going to happen in the form of decarboxylation. Okay, we're getting rid of carbon dioxide. And that's the other way we knew this was aerobic, right? I spy with my little eye a little bit of oxygen. Carbon dioxide only has 1 carbon in it. We have to get rid of 2 of those. Where does the carbon dioxide go? Breathe it out, right? Remember, this is our link between cellular respiration and ventilation. We don't want to store that up in our cells because that's bad for us, so I'm going to ventilate that out. All right, now what I see on here is a lot of really important stuff. Firstly, I see some serious couponage. I see 3 NADH, the most we've ever made, as well as 1 FADH2. Okay. The first time we've made one of those, it's the same sort of thing, right? It's just another type of coupon, one of those electron carriers. Moss coupons. I also see they do get a little bit of ATP out of the deal. Yeehaw! Like the smallest amount ever. Okay, but it's still not 0, which is what the prep step gave us. So it's still better than that. Poor little prep step. Okay, so this is pretty good. But it's about to be even better. How many times do I go through the citric acid cycle? Twice, right? Because remember, I have 2 acetyl-CoAs. So I'm going to do 1 cycle, 2 cycles, 1 for each acetyl-CoA that I have. These numbers just got pretty legit, right? So how many NADH do I have? 6. Okay. How many ATP do I have? 2. Okay. How many FADH2s do I have? 'Kay. Now we've made some stuff. right? Those are a lot of coupons. Look, I'm counting, not grammaring, right? So now we can get an inclination of why the citric acid cycle is so very important. Okay. Not necessarily for the ATP. It's not bad. We made that exact same amount in glycolysis, right? So we would have come a long way to do something we did a long time ago. It's a great bonus prize. Okay. But what we did do here is make a whole heckin' ton of coupons. They were coming out of here with 8 total, right, of different kinds. And that's a lot that we can use. Our piggy bank is now officially full. So we've done in one whole stage something that we weren't able to do in all of the other stages put together. That's a big deal. Okay, we needed oxygen to do it, right? This is an aerobic process. Okay, but it's a big deal to have done it. Does everybody see what we've done here? Any questions about the actual, the actual cycle that we've drawn and all the pieces that we've pulled out of it? Okay. And remember, this is a cycle, right? So when we're done, we've left oxaloacetate. Okay, so it can keep going, assuming we have more acetyl-CoAs, right? If we're breaking down sugar and all that business. We're done with it for now. Okay, but this cell could keep going. All right, so here's our summary table for this. Of course, we made more CO2, but we don't care quite as much about that as we do our energetic compounds. Right, those were our goals to keep track of. Okay, many, many coupons. Right, so our ATP had the same net as glycolysis. Which is not bad. Okay. What we really love here, coupons. Need our own TLC show. It's still a thing, right? That whole extreme couponer thing, right? Yeah. Oh, yeah. All right, so we're officially ready. Okay. We've accumulated all the coupons we need to finally make actual ATP, right? Because we haven't made diddly. And we made 2 in glycolysis and 2 here. And that ain't going to fuel anything. Everything we've done up to this point, you guys have been at least somewhat familiar with, right? This is all stuff that we experienced in lab. So don't forget that your recitation packets from lab will also make very helpful study guides for you. Any questions about anything that we've done up to this point? Because we're about to embark on some new territory. Okay, so the last 2 stages all belong to a process called oxidative phosphorylation. Okay, so as we go into this, even though it's new, our goals remain the same. Okay, you want to know what's the start and the end of here? Okay, where are we in the cell? Do we need oxygen for it to occur? And What are the energetic compounds involved in the process? Okay. So we want to keep our focus, and that'll keep us from becoming too overwhelmed. Okay, here we go. Maybe. So here's the key. Remember, we've been saving our coupons this whole time. And the coupons are the key to making this whole process work. Okay? These guys are going to turn this whole process. Okay? As we'll find, this is going to run down what's called the electron transport chain. Okay, so our NADH and our FADH2, remember, are called electron carriers. Okay, so what we're going to do is we're going to break them. Okay, remember, when you break molecules, you get energy out. In this case, our energy is going to be these electrons. And these electrons are going to act as little smugglers now. Remember, our goal is to cheat active transport. That's why they're coupons, right? And so as electrons, they're going to cheat and smuggle protons across the membrane. And by doing this, we're ultimately going to power a turbine that's going to make ATP. We're going to do this in a two-step process. Okay, so for every step we do, I'm going to define how it works, and then I'm going to draw through the steps with you. So that way, no matter which way you learn, okay, we're going to nail through it together. Still with me? So it's time to turn in those coupons. So the first step of this is that ETC, electron transport chain, aka we're going to use our coupons. Okay, the first step of this is where 90% of the work happens. The second step is where the ATP comes in. Okay, so remember, we're in the mitochondria. And once you enter Alcatraz, you never leave. And the goal here is we're in the Crease day. Remember, the Crease day are those folds or those countertops. Lots of countertops, lots of space to work. And so as you find, we've been talking about this being an electron transport chain. That's how I'm going to draw it. Okay, so up to this point, we've been talking about doing things like active and passive transport. We've always done it across the plasma membrane. Okay, but as we're going to find, a membrane is a membrane is a membrane. Okay, so we're going to do it across mitochondria membrane instead, right? Because these are the countertops. This is the membrane we want to be on. It's going to look and function exactly the same way. Okay, this membrane still separates two spaces. We're going to set up a gradient between these two spaces. And the electron transport chain, aka these proteins, our favorite biomolecule, okay, is going to help with facilitated transport. So they're going to function exactly the way we expect proteins to function when we're doing transport. We're just putting it on a different membrane than we've done before now. Okay, so as we do this, remember I said we're going to break our NADH and our FADH to open by getting our electrons out. Okay. Remember, anytime we break bonds, these are catabolic type reactions, so it's going to be spontaneous. All right, we're going to answer another question here then. Okay. Remember, we're dealing with electrons and ultimately protons. Here's my lazy electron. Okay. Protons are actually hydrogens that are charged. We'll deal with both of these in our drawing. Remember, definition first, drawing second. So if the definitions feel frustrating, don't freak out yet. We'll do our drawing second, so we have both ways to learn. Okay. Remember, the key here is if we add a bunch of electrons to cells, this isn't great. Okay? It's going to be good for moving stuff around, but we don't want to leave them there. Right? Electrons are what we use to make your muscles twitch. Okay? So it makes your muscles move. Okay? Protons and electrons that make your hearts pump. Okay? So while they're great for a few seconds or a few instances, you can't just leave them there. Okay? Not great. We can't store electrons in cells and in tissues. So when we're done with our electrons, we have to get rid of them. They have to go away, go bye-byes. So oxygen is what's going to allow us to do that. Okay, so this is an aerobic process. And we're going to find at the end here, I'm going to combine an electron and a proton. I'm going to solid out that charge. Just make a plain hydrogen ion. Be quiet and shushy. We'll walk through how to do that. But for now, right, we're defining it. And then we'll take 2 hydrogen ions, 1 of the oxygen ions, and make water. Okay. This is one of the reasons when you breathe out, remember our second law of thermodynamics, breath is wet. This is where that water comes from. One of the places that water comes from. Okay. This still feels scraggly right now. Cool, we're going to do it again. Okay, so for now, we can just understand that we're going to use oxygen. Any questions about any of our definitions? All right, here we are, we're finishing up, right? This is the first stage of oxidative phosphorylation. So we're not actually going to make ATP yet, okay? What we're going to do, okay, is build up, okay, so we can work towards it. Okay. So what exactly does the electron transport chain do? Okay, our goal, I'm going to draw right below here, is to pump protons, right? That's what a proton looks like. A charged hydrogen atom from one side of the Crease stay, so one side of that countertop, the mitochondrial matrix, to the other side of that countertop, the intermembrane space. Just think of the countertops in your house. They separate your house into spaces, like the kitchen and living room. Okay? Mitochondrial Crease does the same. Right? Separating the mitochondria into two separate spaces. Its kitchen in the living room is the matrix and the inner membrane space. Our goal, remember, is to create a high concentration gradient. This is going to be really important in the very last step. Okay, now think normally when we create or go against the concentration gradient, okay, I usually have to pay a toll or I have to pay a fee to do that, right? We pay ATP. I don't want to do that. It defeats the purpose. If my goal is to make energy, I don't want to spend energy. Right, so this is where my cheating comes in. Okay. I'm going to rely on my charges. I'm going to combine some positive and negative charges temporarily and smuggle or hide my protons as they pass across that membrane. Okay, so let's see what this looks like. So there's my crease day. Okay. Just like any other membrane, I'm drawing it just as lazy as I always did, right? This is separating my two spaces, my kitchen and my living room. My two spaces, my matrix, and my inner membrane space. Okay. I'm doing transport, okay, not simple diffusion. I know that any kind of facilitated transport is going to need proteins. This is what makes up our electron transport chain, so I'm going to throw in some proteins on here. But as good as I ever lazily draw them. Electron transport chain proteins. Okay? So far, pretty boring. Right, now let's make a concentration gradient. So I already know that I have to work against one. So I'm going to put some protons up top. A few at the bottom. Here's the goal, remember. I want to continue to move my protons from the matrix, from the bottom, against their concentration gradient to the top, right? That's my goal. And I don't want to pay to do it. And so, coupon time. So I'm going to bring in my coupons. Cash in a coupon. When I cash in a coupon, remember I'm going to break it. Metabolism happens. Very dramatic. Okay. Instead of getting energy out, I'm getting a high energy molecule, right? Coupon. Okay. Remember, this is really important. I have protons. Now I have an electron. Okay? This is why the smuggling works. As my electron passes into here, okay, it's going to take a proton with it. When my electron and proton are together, a negative and a positive is what? I put a negative charge and a positive charge together, what happens? I have no charge, right? Okay, secretly, I have no charge right now. Smuggling. Okay? So, okay, my proton sneaks up. Okay, now, like any good smuggler, okay, Han Solo moves on. Okay, so this is the important of these coupons. At any time we have an electron and a proton together in one of our transport proteins, okay, negative and a positive is no charge. So secretly, we can move that proton across because it's not going to get any resistance. It's not a positive charge. Just for a hot second. Okay, once the electron lets go, it's back to being a positive charge, but not too late. Okay? The trick has already been done. And it moves on with its skivy little way. Apparently they're also very devious. That's how I'm feeling this afternoon. Okay, so now we see why it was so important that we built up this huge piggy bank of these specific coupons. Okay, now note that the electrons are not passing across, right? Because we don't want the electrons to neutralize our protons in our space. We want to build up that concentration gradient. Right? They're just sneaking them across the membrane and then moving on. Right? Just like any smuggler. Right? They smuggle the goods, but they don't go with the goods. Seen enough sci-fi shows, right? Any questions about this step? Now, this still leaves us with a problem, though, right? When I'm done, I do still have electrons. And just because they didn't go to the other side doesn't mean that they disappear. They still have to follow our laws of thermodynamics. And I did say that keeping them in the cell was sort of bad, right? Causes trouble. We have to get rid of them. So here's what we're going to do to get rid of our rogue electrons. The first thing we need to do is get rid of the charges that are left. So our electrons are going to bind with a few remaining hydrogen ions in the matrix. This electron, take the hydrogen. Okay. And not like before, okay, but permanently. We liked it, so we put a ring on it. We've been through so much together. And just like the temporary charge neutralization we saw when we were smuggling them across, okay, we'll get neutral charges here as well. Only now we're married. Okay, so we have straight uncharged hydrogen ions. Everybody see that? It's still a little annoying though because they're in the way. Nothing to be done with them, and you can't just move hydrogen ions around. So, in I breathe, in comes that O2. Okay, with the influx of oxygen, I have H2O. So now, when I breathe out, I can get rid of it. Gone, girl. Okay, so now I've achieved all of my goals for this step. Okay, the first part of oxidative phosphorylation, the electron transport chain. Okay, I've used my coupons. They've broken out some high energy electrons, smuggled across protons against their concentration gradient, so free. Okay. But I've also gotten rid of all of that byproduct. I didn't store it up unhealthily in the cell. Okay, so this is again why this is an aerobic process. Okay, this can't happen if this oxygen isn't around. Any questions about any of that? Everybody see what we did here? Can't say I love the silence. I'll take the thumbs up. Absorbing the drawing. Okay, so remember I said the first step of oxidative phosphorylation had no energy, right? We used our coupons. We didn't actually make any ATP, correct? We put in a lot of work. We didn't actually get anything out of it. Okay. The second stage of that, okay, ATP synthase, also called chemiosmosis, is where all the work comes in. I call it ATP synthase. It's also referred to as chemiosmosis. Osmosis, there we go. Okay, so this is where the payoff happens. Okay. We release all of those hydrogen protons down their concentration gradient. So you can see where the sort of the name comes from. It's a form of diffusion, but with a different chemical. I didn't name it. Okay. Specifically, we're going to pass it through a specific protein called ATP synthase. Okay. It's like letting water rush over a dam. When you let water rush over a dam, it creates electricity. Okay. When we let the hydrogen protons rush over this protein, okay, it spins a turbine and it's going to pop out ATP like candy. I'm actually going to pause there because it's going to take me so long to redraw this. We're gonna end up running over. I don't want to do that to you guys. So we'll start with our drawing on Wednesday.